Like, definitely not. I swear I just watched this last week.
Not everything. Everything's all there. I don't feel like I have like eights. Or more eights closest. Outside. So the second last thing. Yeah, Thursdays.
All right, it's 4 o'clock. Let's get started. Good afternoon, everyone. How's everyone doing today? Good to hear. I haven't looked at you guys' exams yet. I'm planning to grade them all tomorrow. So probably by tomorrow afternoon you'll know your grades. Just a reminder. So remember this class I have kind of the split weighting for the midterms. So whichever midterm you score higher in, that's going to be worth 30% of your grade, and whichever midterm you score less in, that's going to be worth 20%. So the way I have it set up on Canvas is that midterm 1 on Canvas is worth 30%, and midterm 2 is going to be worth the 20%. So if you score better on midterm 2, what I'm going to do is that I'm just going to swap your scores. And so I'm going to put your midterm 2 score in midterm 1 and your midterm 1 score in midterm 2. If you do worse in midterm 2, I'm just going to put it in the second slot. If you do the same, it's just the same. So you know, don't be alarmed tomorrow if it says your midterm 2 score was low, but you feel like you did well. You know, it's probably in the midterm 1 slot. So I do that swap just to help your guys' grades, you know, achieve a higher level. Okay. So yeah, and usually for this class, you know, people score a bit better, or there's a decent chunk of people who score better on the second midterm. So I just wanted to say that just so you're not panicking, you know, when you look at your grade on Canvas. Okay. All right, so plan for today, this is our only lecture this week because we took the exam on Tuesday, is going to be more on error and uncertainty and confidence intervals. So kind of along the same lines of thought as you know, data, statistics, probability that we've been talking about for the last couple lectures. Today will be a little bit more applied to probably what you've seen in your labs up to this point. Yeah, we'll see how to kind of take a data set and compute the confidence interval. Okay. Let's see. Oh, let me say a couple of things about the final exam too, because that's going to approach on us very rapidly. So our final exam, I believe, is going to be Tuesday of finals week in the late afternoon in this class. Final exam is cumulative, but it's not going to be absolutely everything that we covered in this class. And so what you're going to see is that, you know, the exam will probably cover will have equal representation, first midterm stuff, second midterm stuff, and then all the probability and statistics stuff that we're covering at the end. So, you know, I can't test you on absolutely everything. There's just no time for that. So what I'm going to do is I'm going to curate the list of topics that we've gone over so far, and then send out a study guide for you guys next week to help you guys study. Okay. So definitely look at the study guide. If you haven't, I would say it's even more important for the final exam, just so you know what not to study, so that you can kind of be a bit more efficient in how you are planning your approach for study. Okay. All right. Any questions on anything before we get started for today? Okay. All right. So let's go and get started. All right. So topic for today is called error and uncertainty in experiments. Okay. All right, so you guys have probably seen up to this point that whenever you take a lab and whenever you have a situation where you're collecting data on some real life event, right? There's going to be some uncertainty in that in those experimental measurements. Okay. Now that uncertainty comes from multiple different sources. And so on the one hand, the event that you're trying to measure, or the physical phenomenon that you're trying to observe, that itself is partially random, right? So we've talked about that a lot in terms of, if you take something like your commute time, that's always going to be a little bit different, just because there's a lot of random factors that you can't account for in observing that phenomenon. Okay. But also there's uncertainty in the sense that, usually when you're using some kind of measuring device, that also is not a perfect device as well, right? So every measurement device has a limited amount of precision in terms of which it can report its measurements. Okay. So this leads to uncertainty. And so, when you do experimental measurements, what you're going to see is that, a lot of times, even if you're measuring the exact same thing over and over again, your measurements are going to slightly change, right? Okay. And so that's why, whenever you're doing any kind of experiment, the first thing that you learn is that you have to measure multiple different times. So you have to do multiple tests of the same thing, because each time that you measure it, you're probably going to get something slightly different. Okay. I still remember this lab to this day. But when I was in college, one of the first physics labs that I did was measuring the acceleration due to gravity. And all that lab really consisted of was, taking a marble and then raising it up to a certain height and then dropping it. And then we drop that marble probably 50 times. And each time, we used a device that, perfectly measured the time it took for the marble to fall. But this was us literally doing the entire experiment, was just, taking the marble up, dropping, taking the marble up, dropping, writing it down. And so, it was probably the most boring thing I've done ever in my life up to that point. But the results were surprising, not the actual result. So we found that gravity was, 9.81 meters per second squared. But that, our measurement actually did have a lot of variance. And so even when we were careful to raise the marble to the same height each time, our measurement device was pretty well calibrated. There was still some variance, right? And so something that we take as granted as kind of a universal truth, there's still some variance because of, random events and measurement precision. Okay, so today, we're going to talk about, how we kind of quantify these types of uncertainties and, how we go about working with them from an engineering point of view. Okay. Any questions on this so far? Okay, good. All right, so let's talk about how we typically express measurements. So usually, whenever you see measurements reported in some kind of lab report or in some kind of scientific paper, usually it's expressed as a mean plus or minus some variance. Okay. All right, so for example, so let's say we're measuring the length of a certain object, right? Usually you'll see it like this. So let's say it's 25 millimeters plus or minus maybe 2 millimeters. Okay. Okay, so with this notation here, we have an expected value. So we call this the expected value or the mean of the measurements. Okay. So usually, let's say that we took 10 measurements of the length of this object, and on average, you take the average of all those measurements, you get 25 millimeters. Okay. And then this quantity, which comes right after the plus or minus, this expresses the variance in the data. Although remember, variance has typically has units of the measurement squared, and so even though this measures the variance, usually it's expressed as standard deviation. Where standard deviation is just the square root of the variance, but we use standard deviation because it has the same units as our mean. Okay. Okay. So this is very classical, and I think it lends itself very well to kind of very easy interpretation where this basically tells us that our length measurements on average were 25, but it can get as low as 23 or as high as 27 millimeters. Okay. Now, one thing that's kind of implied in this expression here is that this type of expression of the uncertainty kind of assumes that our random variable or our length here is a Gaussian random variable. So if you remember the last lecture we had before the midterm, so about a week ago, we talked about Gaussian random variables, right? So Gaussian random variables are the what we typically know them as bell curves, right? Right. So if we look at the probability density function of a Gaussian random variable, right, Usually it looks something like this. This right here is the PDF, or probability density function. Where remember, for a Gaussian random variable, we have a very clear peak. And so that peak is going to be what the mean is, or the expected value. Right. And then the width of the peak, that tells us a bit about the variance or the standard deviation. Right. And so by expressing our measurements in this form of, mean value plus or minus standard deviation, we're kind of implying, or the implication is that we're assuming that our measurements are Gaussian in nature. Okay. Now, remember, from a week ago, a Gaussian is not the only random distribution out there. There's also a uniform distribution. There's also, beta distribution, basically distributions with different, say, bimodal distribution, right? So this is not the only way that we can express uncertainty in a random variable, but it's just the most common. I think it's the most kind of easily well understood. Okay. And so a lot of what we're going to talk about today is we're going to move forward with this assumption that our randomness is Gaussian in nature, and then go from there. Okay. Okay. So when we have a Gaussianly distributed random variable, basically there's two metrics that we're often interested in finding. We want to find out the mean of our random variable, as well as its variance or standard deviation. Because if we can obtain the mean and the standard deviation, then we can construct its probability density function. We can construct its cumulative distribution function. We'll start to know a lot more from that. Okay. Now the tricky thing is that when you have something that's like a random measurement or a random observation out in nature, theoretically it's impossible to find what's called the true mean or the true standard deviation. Okay. Even for things that you're measuring that in your experiments, right? You're running experiments and you're not finding the true mean, you're finding an estimate of the mean. Okay. And so that's kind of important to always remember that, no matter how many experiments that you do, ultimately the best that you can do is that you're finding estimates for the mean and estimates for the standard deviation. Okay. And so it's important to remember that, your measurements there's limitations to it. Okay. I'll give you a great example, actually. One that's kind of very relevant to kind of this exact moment, right? So let's say that we want to find out the average height of everyone that is enrolled in EGME 308 for this semester. Okay. Let's say that we want to find out that information right now, right? The issue with this is that, not everyone is present in the classroom, right? So the best that we can do is, I can go around and measure everyone's height in the class right now, right? And we can get an estimate of the mean based on the measurements of the people in class. Okay. But not everyone's here today, right? And so, some people are on Zoom, some people, are going to watch the recording later, right? So, the measurement that we get today, it's probably going to be a pretty decent measurement, but it's not going to be the true mean because, we don't have all the data that's available to us. Okay. So that's always important to remember that, usually when you're doing experiments and you're taking multiple measurements, in a scientific setting and an engineering setting, what you're getting is not the true mean, not the true value for these for this data. It's an estimate of the mean or an estimate of the standard deviation. Okay. Okay, and so with that, let's put out some definitions. Okay. And so I'm gonna let's define something called the sample mean. And so the sample mean is an estimate of the mean of a data set or the estimate of the average of a data set based on the measurements or the experiments that we have available to us. Okay. So the formula for the sample mean, we've gone over this before. We went over this on the kind of the first day. It's just that now we kind of have this. It has a slightly different kind of interpretation and meaning. Okay. All right. So the sample mean. So often we call it x bar. Okay. Is equal to 1/n multiplied by the summation from I is equal to 1 to n of xi. Right, so this is the same formula for the average that you've probably been using your whole life. You just add up all of the data entries and you divide it by the number of entries. That gives you the average. Okay, but now we know that this formula here is a sample. Okay, so it's the best estimate for the mean that we can do based on the number of measurements that we have. Okay? And what's implied in this formula is that, the more measurements that you take, and so the higher number your n, the better your estimate for the mean is going to be. Right? So that's why I had to drop the marble like 15 times, for 50 times, because 1 or 2 times was not going to be enough. So we needed to drop it, more and more times in order to get a good estimate for the mean. Okay. Okay. So we have sample mean. We also have sample variance. which again is this, mathematically is the same, formula for the variance that we went over, about a week ago. But it just has a slightly different meaning. And so, instead of being the true variance, we say this is an estimate of the variance of a data set based on the data we have available to us. And so just to refresh your memory, our formula for the sample variance here is 1 over n minus 1 multiplied by summation. I is equal to 1 to n of xi minus x bar quantity squared. Okay. And just like the sample mean, the more measurements that you take, the more experiments that you do, the better your estimate for the variance will be. Okay. Okay. Just recap, up until this point, a lot of times when you're considering uncertainty in engineering, settings or applications, we often like to assume that our uncertainty is Gaussian based, and so that means we have a mean and equal variance on both sides of the mean, right? And if you wanted to estimate the mean and estimate the variance, usually you do so from a data set. So that means taking measurements, running experiments, doing this multiple times. And then estimating the mean and variance from these points. Okay. And the more measurements you take, the better your estimates are. All right. Any questions on this so far? Okay, good. All right, but then that always kind of raises the question, or at least this is a question I always ask, when I had labs, is how many measurements do you need to take for you to be really confident in your estimate of the answer. Okay. Now, if you're doing, experiments or, things in a university lab like this, probably the amount of measurements that you do is just based on whatever the lab manual tells you, or just based on how much time that you have with the, with the lab. So I remember I had a TA, and this was not the same TA for the physics lab. This was a chemistry lab. But I asked, like, how many should we do? He said, I'm only paid to watch you do it 3 times, so you're only gonna do it 3 times. So. But there's when you're not limited in that case, there's always a good question to ask, because this tells you how much, when let's say you're doing this for an engineering company, this tells you how much time and how much money you need to budget for these types of experiments to make sure that the data that you're getting is significant enough. Okay. And so with that, that leads us to kind of the main topic for today, which is called confidence intervals. Okay. All right, so it's a given fact that whenever you're performing measurements, you're performing experiments, the more times that you repeat it, you're going to get more confidence in your results, right? But how do we quantify that confidence, right? So that's kind of the idea with confidence intervals. Okay. Because it's one thing to say that you're confident in a measurement, then it's another thing to say that I am 99% sure that this measurement is accurate, right? Because people like numbers, right? So you want to kind of put a number on how confident you are, so that you can compare that to other situations. Okay. Okay. And so let me give you an example. So when you're talking about confidence intervals, you kind of are defining two separate things. And so on the one hand, you're defining your level of confidence in terms of a percentage. Okay. Okay. And so this percentage is something going to be is going to be some number between, well, it's a percentage. And so it's between 0 and 100%. Okay. And so what this percentage represents is that it represents the probability that if you were to take another measurement of the same quantity, that's the probability that, that measurement falls within the range that you're specifying. Okay. So based on the measurements that you have so far, if you were to take another measurement, you can say that there's going to be a 95% chance or a 99% chance that your next measurement is going to be within the certain interval. Okay. And that's the second part of a confidence interval is the, well, interval itself. And so an interval is defined by, a lower bound value and an upper bound value. Okay. So those are two parts of a confidence interval, is that you need a level of confidence, and you need the interval in which you are going to put it. Okay. So I should have put the example a bit lower. I forgot that I didn't resident define those yet. But for example, let's say that you want to put a confidence interval on your commute time. Okay. Okay. And so one way that you can express this, and a lot of times people express this just naturally, kind of just in conversation, right? And so you can say that, I am 95% sure that my commute time will be between 35 and 45 minutes. Okay. So that's how you use a confidence interval. So you express your level of confidence as a percentage, and then you give your interval after that. Okay. So what that statement's saying is that, if I were to measure my commute time coming to work tomorrow, right, there should be a 95% chance that that commute time is going to be between 35 minutes and 40 minutes. Okay. Now, the important thing or the kind of the pattern that you should notice with confidence intervals is that as your level of confidence goes up, right, or as you increase the level of confidence, your interval is going to get wider. Okay. So taking that same example, so let's say that, say that you're telling, I'm telling that to my friend. So I say, I'm 95% sure. He's like, 95% is not good enough. So give me a 99% confidence interval. What are you 99% sure that your commute time is going to be for tomorrow? It's like, well, if I'm increasing my confidence to 99%, then I have to widen my interval to account for more kind of random events. Okay. So for example, so if I were to increase this, so let's say I want to give the 99% confidence interval, right? If I'm going to express that much confidence, I have to widen my interval, just to account for more kind of random events. Okay? Because let's say that there's a 4% chance that there's some accident on the way to work today, or there's some kind of issue with my car that I need to fix. Right? Oops. Okay, so let's say that, if I increase with this 99% confidence interval, 99% chance my commute's going to be between 35 and, well, let's say between 30 and 55 minutes. Okay. But this accounts for the fact that, maybe there's some kind of rare event that's going to happen on my commute time. And so 99% chance that my commute time is going to be between these two. I'm still leaving it open. It's really hard to have a 100% confidence interval, just because you never know what's going to happen with these kind of random events. So a lot of times you're not going to push it all the way to 100%, but it is possible to get 99%, maybe 99.9% if you really want to push it. For these kinds of things. But it's important to remember this relationship that as your demands for confidence get higher, then the interval will shrink or will widen. Okay. Opposite is true as well. And so if you lower your confidence, if you lower your standards, right? So let's say that maybe you only want an 80% confidence interval. Right. With the lower confidence threshold here, you leave yourself available to tighten your range. Okay. So with an 80% confidence interval, I'm pretty confident that it's going to be maybe between 38 and maybe 42 minutes. Okay. So there's an 80% chance that my commute is going to be somewhere in between those two. Okay. But that's kind of an important intuition to kind of establish now, because once we start getting into the calculation, you'll see this a bit more. But kind of understanding that relationship is pretty. Okay. Any questions on this so far? Okay, good. Okay. All right, so let's get into some calculations. Okay, so how do we compute the confidence interval? Okay, So we have a fairly simple formula here. So one thing you'll notice about probability statistics is that the formulas themselves are pretty straightforward. There's not much to them. Usually what's difficult about probability and statistics is the application of these equations. Okay. Okay. So the first one we have here is a K, where K is our confidence interval. Okay. This is equal to C multiplied by sigma divided by square root of n. All right, so let's define all these terms here. So first we have sigma. Okay, so sigma here, that's the standard deviation. Standard deviation of the data that you're considering. Okay. We're going to assume that we know that ahead of time. N here, this is the number of samples or number of measurements. Okay. And then C, C is a coefficient that depends on the level of confidence that you want in your solution. Okay. So the way that you obtain C is that you usually look it up from a table. Okay. And so let's see. So the table looks something like this. And so on the one hand, you have confidence level. And then the other column here is we have confidence factor for C. I'll just say C on this side. Okay. So there's more comprehensive versions of this table. I'm just going to show you kind of the first few here. But the same trends that we kind of talked about still occur. Okay. So for a confidence level of 90%, right, the value for C is 1.645. For a confidence level of 95%, our value for C is 1.960. For a confidence level of 99%, our value for C is 2.576. And then for a confidence level of 99.9%, our value for C here is 3.291. Okay. Okay, so these may seem like they're very random, very random numbers, and in some cases they are. But remember, up until this point, we've assumed that our random variable is Gaussianly distributed. Okay, so these numbers here, they assume a Gaussian random variable, or Gaussian distribution. And so if you're using a different random model or different distribution to describe your measurements, like a uniform distribution, a bimodal distribution, beta distribution, that's going to change these numbers a little bit. But like I mentioned, the Gaussian distribution or the normal distribution, that's the most common one that we use for engineering measurements. Okay. Okay, and then once you compute your value for K, then your confidence interval is defined by the following. Okay, so your confidence interval, you're going to have X bar minus K, which is less than or equal to X, which is less than or equal to X bar plus K. Okay, so your lower bound is given by X bar minus K, and your upper bound is given by X bar plus K. Okay. Remember, X bar here, this is the sample mean, or that's the best estimate for the mean that you have. Okay. And K comes from the formula that we just described up above. Okay. Any questions on this before we jump into an example? Okay. All right. So let's do an example, just so you can see it all put together. You'll see the computations are not that intensive. It's really just kind of understanding kind of what's going on. Okay. So for this example, let's have 10 different people use a ruler to measure the length of their phone. Okay. And granted, these notes were written in 2019, so these are I think these measurements are small compared to the size of the phone is now. Okay. Okay. And so let's say we collected the 10 measurements, and we'll assume that they're all the same phone. Okay. So our 10 measurements in this case are 8, 7, 7, 7, 8, 7, 8, 7, 8, and 8. I think that's 10. 1, 2, 6, 7, 8, 9, 10. Good. Okay. And these measurements were in centimeters. Okay. All right. Another thing that we know for this problem is that the ruler that was used in this experiment had measurement demarcations in centimeters, but nothing smaller than that. So the precision of this measurement is half a centimeter. Okay. So basically, if you were to look at the ruler, right, the ruler might look something like this. Right? So it might have lines. Right, so maybe this is 4 centimeters, 5 centimeters, 6 centimeters, 7 centimeters, 8 centimeters. Okay. So there were no marks in between. So the best that we could do is round up to wherever the marking is, right? So we didn't ask the participants to to cut it in half or estimate the decimal. And so that's why all the measurements there are whole numbers, because that's the best that we can do given the measurement device that we have. Okay. Okay. So based on all this information, so based on the data that we collected and based on the precision of our measurement device, let's compute the 95% confidence interval for the length of this phone. Okay. All right. Any questions on the setup for the problem? Okay. Okay, good. All right. So to find the confidence interval, we're going to need our expressions from up here, right? And so first thing we have to do is compute the sample mean, right? So we're going to compute just the average of all the measurements that we have. Then we're going to compute the K value based on our standard deviation, the number of measurements, and our C value. And then we'll put it all together for our confidence interval. Okay. But first thing we're going to do, let's compute the sample mean. Okay. So X bar in this case is just going to be the average of all the measurements that we took, right? So we took 10 measurements, and so we're going to do 1 divided by 10. And then we're going to add up all of our measurements here. So we have 8 plus 7 plus 7 plus 7 plus 8 plus 7 plus 8 plus 7 plus 8 plus 8. Okay. So normally you would do this in a calculator or something, so it's a bit faster. You don't have to write out the whole expression here. But if you do all this, or if you're savvy and you see that we have an equal number of 8s and an equal number of 7s, and so the average of this must be right in the middle of them, which is 7.5. Okay. All right, so that's our sample mean. All right, so next thing we're going to do is we're going to compute our K value. So that K is equal to C times sigma times square root of N. Okay. Okay. Now here's where it gets a little bit interesting. And so, for this particular situation, since we know the precision of our measurement device, that kind of sets our precision or our standard deviation right from the start. Okay. Right. So this is a relatively simple case where we're finding confidence interval from something that we're directly measuring. And so in those cases when you're directly measuring something, you want to find its confidence interval. The uncertainty in that case mostly just comes from the precision of the measurement tool itself. Okay. And so luckily in our case, we have that, right? So we know the precision of our measurement tool is 0.5 centimeters. Okay, so we're just going to plug in 0.5 centimeters in for sigma. Okay. All right, but of course there are going to be cases where you don't know what the standard deviation is going to be. Either you're computing the confidence interval of some derived quantity, and so in those cases you're going to have to use the sample variance to compute K, which we'll go over after this. Okay. Okay, next thing we're going to compute is we're going to plug in our value for C. Okay. Now our value for C depends on our level of confidence, right? And so for this problem, we have a 95% confidence, okay, or we want to compute our interval for 95% confidence. And so what we're going to do is we're going to look at the table for 95% confidence and then plug in that value for C. Okay. And so for 95% confidence and for a Gaussian random variable, we have a C value of 1.96. Okay. All right, and then last thing we're going to plug in here is the value for N, which is just simply our number of measurements. Okay. And so we're going to plug in N is equal to 10 measurements at the bottom, and we're going to take the square root. Okay. All right, so we plug all these factors in, and we get a confidence level of 0.31 centimeters. Okay, so now that we have our sample mean, now that we have our confidence interval here, let's put it all together. All right, so to put it all together, it's best kind of stated as a sentence. And so we can say that we are 95% sure or 95% confident that the length of phone is, so we're gonna have 7.5 centimeters minus 0.31. Which is less than or equal to L, which is less than or equal to 7.5 centimeters plus 0.31 centimeters. Okay. And so that gives us a confidence interval of 7.19 centimeters to 7.81 centimeters. Okay. So we're 95% sure that the length of the phone is somewhere in that, based on the measurements. Okay. Any questions on this so far? Just on this example? Yeah.
I'm confused by the precision of measurement in 0.5 centimeters. I still don't really understand what you meant by, you said since the ruler have marks only for centimeters.
Yeah. So because our ruler had marks only for centimeters, and so our ruler went 4 centimeters, 5 centimeters, 6 centimeters, 7 centimeters, 8, right? That means when we measure something, so let's say we're measuring something, we have kind of the edge of our phone that's like this, right? It's somewhere in between. And so, but since we don't have any markings between 7 and 8, we have to kind of make a guess in between 7 and 8. And so, for this one, let's say that we say it's 7, right? But if we say that our measurement here is 7, that means it's it could be anywhere in between these two right here, which is 6.5 and 7.5. So say the precision is 0.5 centimeters. You got questions on this example here? Okay, good. All right, so let's look at this formula a bit more before we kind of move on to the next topic, right? So this confidence interval is a bit wide, right? And so it's kind of a big range from 7.19 to 7.81 centimeters. Okay? One way that we can improve this confidence interval is by taking more measurements, right? And so if you notice, if you look at our value for K here, our value of K will decrease as N increases. Okay. And that aligns with kind of how we understand, experiments and measurements too, right? And so, the more measurements that you take, the more experiments that you run, your confidence in your result is going to increase, right? And in this case, an increase in confidence is expressed as a decrease in this K value, right? Now, the interesting thing is that, if you look at our formula for K, right? It doesn't decrease that strongly with N, right? And so, in fact, our N in the denominator there is not N by itself, but is square root of N. Okay. So that means, if you really want to increase confidence in your solution, you really need to jack up the number of measurements, right? And so let's say that you want to cut your confidence interval by half, right? Okay. Right, so to reduce the size of your confidence interval by half, that's essentially the same thing as reducing the value of k by a factor of 2. And so in order to achieve this, in order to basically double your confidence, it's not the same thing as doubling the number of measurements, right? If you want to double your confidence here, you have to actually take 4 times as many measurements. Okay. And that's all because of that square root dependence on the bottom. So if we write out our equation for k, so our k here is c times sigma times square root of n, right? If we take 4 times the number of measurements, and so we increase n by a factor of 4, and so we have c times sigma, so those on top stay the same. But instead now we have 4 times n, right? So from the square root, the 4 will take square root and become 2. And so this becomes c times sigma times 2 divided by 2 square root of n. Okay. Right. And so that's the way to kind of have that interval, right, or double our confidence, right? And that goes beyond even more than this too, right? So if you want to increase your confidence, you have to kind of be prepared to pay, an increasing premium or increasing price for that increased confidence because that because of that square root in the bottom. Okay. Okay. All right. Any questions on this? Okay. All right. So that's fairly simple case. So when you know your standard deviation or your precision, computing confidence intervals is honestly just a little bit of plug and chug, right? But how do you compute confidence intervals for cases where you do not know the variance or where you don't know the precision ahead of time? Okay, so in these cases, computing k is a little bit more complicated because you're not going to be able to just plug in something for sigma. Okay, so the big difference that we're going to be doing here is that instead of applying a known sigma from the beginning, we're going to compute sigma based on our measurements. Okay. So now instead of being like a true precision or a true variance, we're instead computing our sample variance and taking the square root. Okay. Okay. right? So, that seems like it would be an easy switch, right? And so instead of, instead of using a known value for sigma, all we have to do is just compute it based on our data, which we have a formula for, right? So we have a formula for the sample variance. It was up here somewhere, right? Sample variance was this formula here, right? So we have a way to compute it, right? And so, if it's just a simple matter of plugging it in, right? Then there's, in theory, there shouldn't be too much to this, right? Now, unfortunately, if we're going to go this route, right? Remember, when we take the sample variance of a data set, this itself is something that is not completely known, right? So this is just an estimate of the variance. Okay. And so we're using an estimate of the variance to estimate our confidence in the estimate of the mean. And so it's a little bit too many levels of estimation here. So we actually do have to kind of shift our approach a little bit. So we're still going to use our sample variance. So we're still going to compute that. But the way that we translate that into a confidence interval changes slightly. And we have to make use of slightly different data types. Okay. Okay, so there is how many steps we have here? It is a 4-step process. So I think what I'll do today is we'll list out the process here, and then we'll do an example for it when we come back on from the weekend on Tuesday. Okay, so first step is we need to select a confidence level. And we're going to give that the symbol gamma, right? So gamma here expresses the amount of confidence that we want to have in our interval. And so again, this is our percentage, 90, 95, 96, 97%. But we need to express this as a decimal. Okay. So that's the first thing. And so you want to first express how much confidence that you want to have in your interval. Okay. Okay. Number 2. Step 2 is we're going to compute this fairly simple formula here. So we're going to say compute 0.5 multiplied by 1 plus gamma. And this is going to be equal to what we call f of c. Okay. Okay, so based on the level of confidence that you want, right? Basically, you're going to take the average of that confidence with 1, where 1 being full confidence. Okay, and then that's going to give you this quantity here, f of c, which we're going to use in the next step. Okay. Now the next step here is that we're going to be looking up our value for c, right? And the c is what we're going to be using in our formula for k, right? But we need to look this up in a table. Okay. Okay, so the table that you're going to look up is what's called the t distribution, or the inverse of the t distribution. Okay. So the table is a little bit confusing to use, and so I'll kind of show you how to do it in a second, right? And so if you have the textbook, this T distribution table is actually appendix or table A9 in the appendix. Okay. But this is something I've posted online as well. So, so similar to the table of Laplace transforms, this is something that I took a screenshot from the textbook and then I put it online for you guys. Okay. All right. So the table looks like this. And so the first column is we have f of c. Okay. All right. So the f of c is kind of what we just computed in step 2. Okay. So this has certain values. So I'm only going to list a few here, but just know that there's a lot more. Okay. So this table is massive. It's a huge table. And so it is a little bit intimidating to look at. But first thing you're going to do is you're going to go to the leftmost column and find your value for FC that you computed in step 2. Okay. Okay. All the other columns here are going to be, what we call the degrees of freedom. Okay. And so there's columns for 1, 2, 3, 4, 5, 6. Okay. Okay, and then in these columns, we're going to have different values where each of the values in these columns will tell you the value for C for that given situation. Okay. Okay, so for instance, the first column here, we have 0, 0.32, 0.73, 1.38, and 3.08. Okay. Second column, I'll write the first 3 columns and then we'll kind of stop and discuss. Right, so second column will be 0, 0.29, 0.62, 1.06, 1.89. Okay. Third column here, 0, 0.28, 0.58, 0.98, and 1.6. Okay. Right. And then it keeps going and going and going from there. So I don't want to write the rest of it down just because then it becomes a game of just writing this table. Okay, but I do want to draw your attention to some trends that you see here, and then we'll get to kind of what the degrees of freedom. Okay, so first thing we're going to look at here is we're going to look at the behavior of the table as we progress downwards, right? And so let's look at just a single column here. So let's look at the column for 1. Okay. And let's see how the values for C change as we go down. Okay. Okay. So as we go down here, we can see that our value for C is increasing. Right. Right, and then as you go down the table, that correlates with the value of f of C also increasing as well. Okay, and so if we look at our column for f of C, right, as we get lower and lower down the table, that corresponds to higher and higher levels of confidence. Okay. And so that makes sense, right? And so if you compare this trend to our value for C from the previous case, right? And so we look at our previous value for C, I'll go back down in a second, right? And so as our confidence level went up in our previous example, our value for C also increased as well. Okay. So you see that exact same behavior here. So you see that, as we increase our confidence, our C value is going to increase as well. Okay. Okay. Now, what do the degrees of freedom mean? So the degrees of freedom is just another way to tell you how many samples that you have for a given data set, okay? And so the formula for degrees of freedom all it is just equal to n minus 1. Okay. So basically, the more measurements that you take, the more degrees of freedom that you okay. And if you look at the trends, and so if you look at the trend of this table as you go to the right, right? And so as we go to the right, you know, that's, you know, accounting for an increased number of measurements, right? And so as we go to the right, more measurements. Right? Our value for C is decreasing, right? And that makes sense, right? So as the number of measurements goes up, then our interval gets tighter and tighter. So that means our C value is going down. Okay. So I think this will make more sense kind of once we do an example, but you know, we'll have time for that on Tuesday. But any questions on the T distribution table before we finish this up? Okay. All right, so that's step 2. Okay. Thankfully, step 3 and 4 are pretty short, and so I'm going to write them in 30 seconds each. Okay. Step 3 is to compute sample mean and sample variance. Right. So we had formulas for that back above, right? And so that's based on the data set. You just average it, you compute the sample variance. Okay. And then the last step is to compute K. So K here has the same formula as before. So we're going to take our value for C, except we're taking our value of C from the table in step 2. We multiply it by the sample standard deviation. So we take our standard deviation, we take our variance, we take the square root, and we divide all that by the square root of n. Okay. And that gives us our confidence interval K that we can use same way we did. Okay. All right. Any questions on this before we wrap it up for the week? Yeah.
How big is this table normally? Because like if you did 50 samples of the marble, then they're enough for 50.
It's huge. It's a huge table. And so I think it's posted on Canvas right now, so you can take a look. But yeah, there's a ton of different. All right. All right. So that's all we got time for today. So thank you guys for coming today. I hope you guys have a good weekend. I will have your midterms ready for you on Tuesday. So you can come by class and pick it up then. But hope you guys have a good weekend, and I will see you guys next week.
Something else. There's a final about. It's more like because yeah, so I'm like, well, I don't know if it's more like after the.
Professor,
Yeah.
more elective classes open up.
Yeah, so I think we are gonna post more because right now there's only 8 on the schedule right now. And honestly, if you haven't taken fluids, your options are pretty limited.
That's yeah.
Yeah, so and the department knows that, so I think they're probably gonna post more. I think
Okay.
probably maybe 2 or 3 more electives.
Do you have any idea of what they'll be?
I have a hunch, but I don't want to say because I don't want to get people's hopes up.
What would the hopes up be though? You know, I won't say anything.
So there is a like an aerospace class that's in the works right now.
Oh yeah,
That
for
one
the
could be-
Spark Center, right?
Yes,
Yeah,
yeah,
yeah.
okay, so people know about that.
Yeah.
Well,
Well, Dr. Wong's talked about it.
okay, if he's talking about it, then it's probably.
Yeah.
So that one I'm pretty sure is gonna be posted. I know we're probably gonna try to post one in the kind of like strength of materials type of area.
Okay.
So maybe like plastics or failure materials or composites or something like that.
Okay.
Maybe one of those type of classes. I would say those two are pretty safe.
I imagine for the aerospace, you need fluids, right?
Yeah. Yeah, so that doesn't really help the issue, so I'm pretty sure, like, because that class we have to offer, because that's part of the Sparks program.
Yeah,
And then the other, I'm thinking we're probably gonna post two more in kind of like, failure materials.
Yeah.
Composites, something.
you do advising by any chance?
I do. Yep.
Okay. I had a question, so I might be I'm applying for the Spark Center internship.
Okay, awesome.
I don't know if I'll get that, but assuming I do, the main issue I'm running into is I don't have fluids yet, and I'm gonna be in senior design next year.
Okay,
So if I were to get the position for the fall, I would have to put that on hold. But the problem is, I just need fluids, and I don't know how I can do that from now to then, because like, I don't think anything's offered over the summer.
yeah, fluids is tough to find over summer. I think probably your best option would be Cal Poly Pomona.
Really?
So their mechanical engineering department offers a lot of summer courses.
Yeah,
I took a brief look at their offerings this summer. I don't.
and can if I go to Fullerton, can I take a class at Cal Poly Pomona?
You could. Now, the difficult thing is getting it to count for fluids here, so.
Okay,
So usually our policy is that because fluids is upper division, we only allow outside credit if it helps improve your graduation.
okay.
Now,
That's actually good to know, because like, if I did this internship, like, it would throw off my graduation a ton if I don't get fluids. in it,
Yeah,
So.
yeah. So the thing with fluids, actually, it does actually improve graduation a lot of the time.
Yeah,
Because then it allows you to take heat transfer in the spring, you take heat transfer in the spring, then you take 306B. And then,
Right.
then you can take the labs a bit sooner too, so. Yeah, do you know how to make an appointment with us? So there's a link.
I did a walk-in last time, I
Okay.
never actually scheduled.
Okay, yeah, I'll send you an email, probably
Okay.
later this evening, and then, yeah, I'll look at your TDA and see if there's any possibilities. With Sparks, we might make an exception though, just because that's kind of a special thing, but
Yeah,
that's kind of unprecedented, because this is the first year that we're doing it.
yeah.
So yeah, I'll take a look, and then I'll talk to the department chair, see if we can accept fluids outside just for that.
Okay, that'd be great, cause like my other thing was, I was thinking like, if it was over the fall, cause you know how like you record your lectures and post them?
Yeah.
I don't know if any of the fluids professor did that, but I was gonna ask if I could like potentially take it online, like I was gonna talk to Dr. No about that.
Yeah,
Just cause like that is the only thing that would hold me back, but.
yeah, I think because the Sparks is so, I would definitely talk to Dr. No about taking fluids this summer. I mean, I'll talk to him for you for that too.
Okay, that'd be great,
For
but that's like if I get the internship, like
Yeah.
obviously not the
Yeah.
design story.
Yeah, no, for sure. But yeah, I think that's an interesting case. I think that's something to look at.
Okay,
Yeah, especially because, because I mean, we want our best students in that internship too.
yeah,
So, yeah, I think it's something that we would consider something we look at.
I appreciate that, Professor.
Yeah,
Thank
of
you
course.
so much.
Mhm.
Have a good one.
You too.
Have a nice weekend.
You too.